Okay, well, hello at home. Here we go again. I'm just finishing off really complex numbers. We've pretty well done all the basic theory of everything. Now it's just a matter of seeing all the questions you can deal with, which is your textbook and past exams and that sort of thing. Anyway, let's deal with this thing here. This is a modulus question. Modulus of that is less or equal to modulus of that, and we'll see what this all means. We know, as usual, we let the z be x plus iy. In which case we have the modulus of x plus iy minus 1 plus 2i. That much is pretty straightforward. And then I will collect the real bits and the imaginary bits together. And you know that if you have, if we had a plus ib, the modulus of z is root a squared plus b squared. If z equals a plus ib. And we'll just do the same thing with this here. This is the same as the square root of that real part squared plus that imaginary part squared. And we're all looking good so far. Now we're just going to have to rearrange this and solve this and try to get it in its simplest form possible. If you square both sides, all the square root will go away, and we'll be left with what's in underneath. And then just expand the brackets everywhere you can, all the squared brackets. And if you do that, you should get something like this. That one should give us x squared minus 2x plus 1. Y squared plus 4y plus 4, x squared plus 6x plus 9, y squared 4y plus 8y plus 16. So that's just a matter of squaring and expanding brackets. And now lots of stuff will disappear. If I take away x squared from both sides, that goes away. If I take away y squared from both sides, that disappears. Now I've just got single x's and y's, single x's and y's. I'm going to rearrange that and I'll get a straight line of some sort. So it's just a matter of doing that. I think I'll keep my y's on the left and put my x's on the right. So my y's on the left, I've got 4y here. I've got 8y. And I'm going to, well, I'll do it that way anyway. I'll keep the y's on the left. 4y, take away 8y, will give me minus 4y. Put my x's on the other side. I've got 6x minus 2x, that's going to give me 8x. Now the numbers. I've got 5 here. I'll take 5 away from both sides. I've got 9 and 16, which is 25. So I'll do that. I've got 25, take away 5. 4 minus 5. 5, yep. Okay, so I end up with minus 4y less than or equal to 8x plus 20. Now I'm going to divide everything by -4, but be careful with inequalities. When you divide by negatives, you have to reverse the sign of the inequality. So dividing by -4, I will get y is bigger than or equal to -2x plus -5. Just be careful when you're dividing by a negative number. You have to reverse the sign. And we end up with this expression. Y is bigger than or equal to that. And that is, when that modulus is less or equal to that modulus, you get this value for y. Let's just see what this actually means. I'll draw the picture on an Argand diagram and you'll hopefully see what this means. Over here, -2x, -5. So it goes through -5. The reals and the imaginaries. -2x means it's doing that. And if x was equal to 0, y would, we don't know, we need the other one. If this is 0, 5 over there, we're going to get negative 2/5. And because y is bigger than that, or equal to it, bigger than that will be up here. That would be the picture that goes with that, which is where this modulus is less than this one. But what this actually has happened here, at this stage, this line here, if you square both sides, you get that and that, and you get that and that. Now, normally, a modulus of just something when it's just by itself is a circle. With a center, this one will be a center of 1, -2. This one will have a center of -3, -4. Let me just plot those circle centers. So 1 -2. The scale is funny, -2/5. Did I do that right? Let me just check that. 0 equals 2x, 5, 5 over 2. Oops. That should be a 5 over 2, not a 2 over 5. That's right here. Oops. Right. That's what it should look like. Where was I? I'm just going to plot this circle. We've got 1, -2. That's -2. This 1 would be about there. 1, -2 would be about there. And this center is at -3, -4. 3, -4 will be about there. If you imagine those are the center of what these would be circles, this line here between the two is where the distance to that line from either of these circles, so if you went from anywhere along that line, I need a different color. I hope this color comes out on the screen, because I know the red doesn't go so good. If we were at this point here, that's in green, along that line that we've just found, then the distance from the center of that circle would be the same as the distance from the center of that circle. So this line represents all the points where the distance from the center of that circle is the same as the distance from the center of that circle. It's the line that's halfway between these two, so that if you did a straight line between them, that would be exactly halfway between those 2 points. And that's what you're sketching when you do that. And then just the bigger than or equal to is just telling you you're either above it or below that line. Right. That's the first example question that I wanted to do today, and you'll see that, and there's one like that on that assignment, which I've just sent you an email about doing and sending in using Canvas. I'll pause the recording there, and then I'm going to put up a harder question, and you might like to have a go at this harder question, and I'll give you 10 minutes or so to think about it, and then I'll go through that as well, and then we'll just see if anyone's got any questions about anything in particular about all the other stuff you'd like me to go through. Okay, so I'm going to pause the recording here. I'll rub this lot out because you'll have a recording of this, and then I will put up another question, a little bit trickier perhaps. Okay, I'll just pause the recording. Okay, now I'm looking at this question 101, and it's find real numbers A, B, C, and D such that that and that are roots of that polynomial there. Well, from the conjugate root theorem, you know that if that is a root, then 1 plus root 3i is also a root, and if that's a root, then 1 minus root 2i is also a root. So we can just write that down to start with. Conjugate. So we've now got 4 roots of this z to the power 4, and therefore we have the factors. And if you expand all these factors, just whatever the numbers are in front of it, you'll be able to just read off what A, B, C, and D are. I might leave you to do that because you can, you just multiply them all out. You might turn them into difference of two squares. We might write it slightly differently, just to do our difference of two squares method. You've got Z minus 1 minus root 3i. You've got Z minus 1 plus root 3i. Z minus 1 plus root 2i. Z minus 1 minus root 2i. Just A minus B into A plus B. Just expand all that, and you'll find out what A, B, C, and D are. I think I'll leave you to finish that bit off. And I'll stop the recording there. And if you feel like having, okay, here we go. 3 parts. You can bet the first one will be the easy one, and then the middle one will be the medium, and the last one will be the hard bit with this sort of question. But once again, we're starting off with Z equals, this time cos plus I sine theta, so something we're familiar with. First part, show that, just find that in rectangular form. So for part A, we've got Z, which is cos theta plus I sine theta, Z, plus. Now, Z to the power -1. Well, if I write this out, normally I would just write what it is here, but I'll do cos theta plus I sine theta power -1, and that is cos theta plus I sine theta plus, you can just bring that in next to the angle, cos -theta plus I sine -theta. Now, that's cos theta plus I sine theta plus cos theta. That's because cos of negative theta is the same as the cos of theta. This will be minus I sine theta. The sine of negative theta is minus the sine of theta. And then those bits go away because they're the same. And we get 2 cos theta out of that. Reasonably straightforward, part A. Part B, using Binomial's theorem, well, I used it once just here, Binomial's already, I'm going to use it again now, show that Z cubed plus Z to the -3 is that lot. I have a feeling that's very similar to what we just did. Z cubed plus Z to the -3. That is cos theta plus I sine theta cubed plus cos theta plus I sine theta to the -3. Now, Binomial's theorem, or if you turned it into Euler's form, but we were told to use Binomial's theorem, so I will. But that just means we get 3 times that. We just get -3 times that. So we just get cos 3 theta plus I sine 3 theta cos -3 theta plus I sine -3 theta. In fact, it's exactly the same as the first part. Strange to ask you the same question twice. But anyway, there we go. We're going to get cos of 3 theta plus I sine 3 theta plus cos of 3 theta, because cos of negative is the same as cos of positive, minus I sine 3 theta. For the same reason, that's minus, we end up with 2 cos 3 theta. That's the same. Right, there's the first bit. That's the first solution. That's the second bit. That's part A and part B. Done. Reasonably straightforward. The hard bit will probably be this part C. So let's take a bit more time with part C. Here we go. Hence, the hence is important. They don't write hence for fun. They mean you do have to use parts A and B to do this. If it says hence or otherwise, you can do it whatever way you like. But if it says hence, you make sure you use whatever has gone before. Right, using the binomial distribution of that. Well, we'll do a binomial distribution of that then. Here we go. Z to the -1 power 3. equals 1. For binomial distribution power 3, we get the coefficients 1, 3, 3, and 1. Here we go. We're going to get one lot of the first one, that's z cubed, plus 3 lots, z squared times 1 over z. Rather than write z inverse, I'm writing 1 over z because I know I'm going to be dividing them out a little bit. There's 3 lots, z, 1 over z squared, plus, I don't have room before my board runs out, 1 over z to the power 3. So this is now just simplifying each of those terms. Z cubed plus 3, 1 of the z's goes away, I've got the 3z there. That will give me plus 3, there'll be a z on the bottom. Plus 1 over z cubed is z to the negative 3. So there's my 4 terms that I've got. Not looking much like this yet. Let me do something though. What I did before was z cubed plus z to the negative 3. I did that there. I got that. So let me make this bit is presumably okay, but the hard bit must come now. Then I think the first thing is write this out with different groupings. So we're going to get z cubed plus z to the negative 3. And I did that because I remember it from part B. And here the 3 is in common. Z plus z to the negative 1. Now I know what they equal to, because that was part B. They equal that. And that's 3 lots of part A. So part A. Over here was part A, 2 cos. That's 3 lots. 2 cos 3 theta. Right, I've done the binomial expansion of that, and I've got that using parts A and B. But it still doesn't look like what I've got here. I still haven't quite got something that looks like that. And this is the extra bit that you have to think about. You've got a cos to the power 3 here. Well, I've got the 3 theta. I can see that. I've got the cos theta, but I don't have a power of 3 part of it. Here's how I think you get at it. There may be other ways of doing it. When you've got that there, we do the binomial expansion, we end up with that. But also, z plus z negative 1 cubed equals. Now I know what z plus z to the negative 1 is. That was part A. That was 2 cos theta. And that is 8 cos cubed theta. So you can either think of that as being that, the binomial expansion, or you can think of that as being that. There's 2 ways to deal with it. And because I've just done the same, that's been using the same thing twice, that means that must equal that. Let's divide everything by 2. And there we've got to get it. As cos 3 theta equals something. So I've got to get that by itself. That's it. And we've finished. So the last bit was, you know, quite a bit harder than the first 2 bits, which were reasonably straightforward. Yeah, there we go. That's I will pause there, let you think about that and how far you got with it. And that's all I intend to do as examples today. If you've got questions about anything, let me know. I'll still be here, and we'll just see how you go. So send me emails, chats, whatever you want to do, and if you want me to do any. Otherwise, you're just ticking along and ask questions if you need to. I will stop us there. Oh, hold on. I'll pause the recording.